the relationship, the memory, is expressed in terms of linkage between probability distributions. This is the idea. You know, you may say that this is complicated, and then you will see that it's not really. Another thing that you may say is, how can I define a variable, which means several outcomes, random variable, if I refer to only one time step? You may say, at time t, I have just one observation, so how can I define a random variable at a fixed time? So you may think that it's easy to define a random variable for several times, because you have many observations, one at each time, but it may seem like impossible to define a random variable at each time step, because you have just one number. But you have to remember that a statistical process means that you don't have a fixed outcome. You have an outcome that is an observation. So if I go today on the Po River, I measure the river flow, and this is my outcome. But if I measure the river flow again, I get a different outcome, because there is uncertainty in my measurement. It's not a deterministic measurement. It's a random measurement. There is uncertainty, for instance, the error of the instrument, of the measuring instrument. So it's indeed true that even if you fix t, you may get several outcomes for q at time t, depending on what? Depending on the measurement technique that you use, depending on the type of uncertainty that you have. So you have to consider that when you assume that a measurement, a variable, is random, it means that there are several possible outcomes, and what you see, what you measure, is just one of them. This is something that you have always to consider. If you use a deterministic model, then your model computes an outcome, and that's it. And you assume that it's perfect. But if you have a statistical model, then the statistical model should allow you to get several outcomes for each observation. So it's not a problem to define a random variable at each time. And what you see is just one of the possible outcomes, what you measure. Okay, so basically we are not talking about a random variable, we are talking about a family now of random variables. So let me say, if I want to represent 1 year of river flows, I am considering 365 random variables. And this is called, the correct terminology is family of random variables. So the trick is to shift from a random variable to a family of random variables. Okay, so there is a precise term in statistics to identify a family of random variables, and this term is stochastic process. Let me write it down. It's a nasty terminology because stochastic is, you know, it seems something very, very difficult. It's not difficult. You will see that in mathematical terms it's much easier than a linear reservoir. But this is the term, stochastic process. Here it is. So at the exam I may ask you, what is a stochastic process? And I don't understand why the students invent very complicated definitions. What you just have to say is, it's a family of random variables. Stop. This is a stochastic process. If you go to Wikipedia, and just look for stochastic process, there is written, if I well remember, it's a collection of random variables. Same thing. Just say it's a family of random variables, and that's fine. You don't have to invent something very complicated. This is a question that I frequently ask, so just say it's a family of random variables, that's it. And now you may say, look, this is complicated because I have several probability distributions. Okay, let's say that one of the first assumptions is to assume that the probability distribution doesn't change. The parameters may change, but the general shape, we will assume that it's always the same. You can change the parameters, but if you assume that it's the same distribution, then... Okay, now the very practical question is, okay, we understood that you want to teach us what are stochastic processes, so how do they work? How can we reproduce memory by using this idea? So now let me turn to the practical issue, and first of all, let me introduce to you the problem of quantifying memory, because you know, maybe that your data don't have any memory. So if your data don't have any memory, you can solve your problem of generating data just by using the concept of one random variable with its own probability distribution. You already know how to do that. So let's suppose that you have to generate rainfall data. Rainfall usually has very limited memory, especially if you look at rainfall, like weekly rainfall or monthly rainfall. The memory is very weak. So if the data don't have any memory, you don't have to use stochastic processes. You just fit a probability distribution and you generate outcome from the probability distribution. That's it. But, so it's important to be able to say if there is memory or not. So let me very simply introduce one. There are several methods to quantify if the data have memory, and we will use just, I'm introducing just the most frequently used. First of all, let me say that if the data have no memory, they are said to be independent. What does it mean, independent? It means that any outcome from the process that you are considering is not affected by the previous ones. There is no impact of each outcome on the previous and subsequent ones. Okay, this is very simple. Like tossing a coin, there is no impact. If you get a net, then the next trial is not impacted. So this means that the data are independent. Conversely, the data are dependent. So we have to be able to quantify dependence. And how to do that? One simple, very simple method is to use correlation, to measure correlation. What is correlation? I'm not defining what is correlation, I'm just telling you how to compute it. Because it's much simpler just to speak in practice. And to define correlation, I have to define the correlation coefficient. And let's suppose that you have n observations QT, river flow. This is my preferred symbol for river flow, Q. In the international literature, sometimes you find also R. I use Q very frequently. And so how to compute the correlation coefficient? First of all, let's indicate it with the letter rho Q, because it refers to the random variable Q. And the correlation coefficient is computed depending on lag, which I'm defining now, L. And I'm defining now what is. So, this is equal to 1 over n, which multiplies a ratio at the denominator we have sigma square Q at the numerator we have the summation from t equal 1 to n of u t plus n minus mi q multiplied by q t minus mi q. And the summation is extended from 1 to n minus n. Sorry, I forgot to put the minus n before, and that's it. Okay, so you may say it doesn't tell anything to me, this relationship, but indeed, if we look at this relationship with a bit of detail, you may get important information from it. And first of all, this coefficient, how it is derived. So let's see. First of all, you get the observations and you subtract the mean value. Okay? And you multiply by them two subsequent observations minus their mean, which are displaced n time steps apart. So basically what I'm doing is, if I have an hydrograph like this, this is Q, T, this is T. What I'm doing here is, first of all, compute the average, Q, and then I multiply this segment here by this segment here, and their distance is L. This is what I'm doing, and this is a summation. So I'm moving from the beginning of the hydrograph to the end, because it's a summation. And given that I subtract the mean, some of the observations are negative and some are positive, because you see, when you are here, this is negative. So basically, I take two observations, difference with respect to mean, that are distant each other. The distance is L, and then I multiply them and I move forward with the summation. Because don't look at the denominator. The denominator is a constant, okay? So what matters is this multiplication here, and also the 1 over n is a scale factor, it's a constant. So what happens here? And let's assume that L is 1, for instance. If it is 1, it means that I am taking multiplying any observation by the subsequent one, and then I'm moving forward. And look, in this case, what can you observe? That the two quantities that you multiply very often have the same sign. Either both are negative or either both positive. Why? Because this is a regular hydrograph, and therefore you start from below the mean, and you stay below the mean for a while. And if you multiply two quantities that are below the mean, they are both negative, so their product is positive. And then you get around the mean, you just have one term in the summation that is negative, but then you pass above the mean. And above the mean, both terms are positive. Again, the product is positive. And then you get again below the mean. You have just one term in the summation that is negative and again positive. So what can you conclude? That this coefficient is positive. Because the vast majority of the products here are positive. Both terms are positive or both negative, which means that the result is positive. So this coefficient becomes positive if you have a regular hydrograph with memory. Because the fact that it's regular means that there is memory below the mean for some time, above the mean, and it remains above because it has memory, and then again below the mean. So this term is positive. Let me make another example now of an independent variable. If you had an hydrograph made by independent observation, what would you expect? Something like that. And then the mean is this one. And when you compute this summation, you have a regular alternance of positive and negative results because they randomly shift above and below the mean, randomly. So at the end, this coefficient is 0. Because this product here, the summation includes positive and negative terms randomly. The result is 0. So the next question by you could be, is there a possibility for this coefficient to become negative? And I would say yes. Let me make this example, which is not very common in hydrology. Let's suppose that you have an hydrograph that is done in this way, and then you have the mean value here, and you have a regular oscillation from positive to negative to positive to negative to positive to negative. So the product is always negative, and the coefficient becomes negative. This is not very common in hydrology. Sometimes we find negative correlations in rainfall because, rainfall, you may expect that if today is very rainy, tomorrow is a dry day. But not always, not in all the climates. But especially in summer, this happens. In some climates in summer, this happens. So what is our conclusion? The conclusion is, if you have memory, the coefficient is positive. If you don't have memory, the coefficient is 0. If you have a regular alternance of positive, negative, it's again memory. We call it negative memory. The next question by you could be, what are the extreme values? You said positive, negative for the coefficient. There is an upper value or a lower value. Yes, there is. And I would like to propose to you to try to compute this coefficient for the data that I gave to you. This is very easy to compute in R. You see, it's very easy. It's just a multiplication of vectors. And if you try to compute this coefficient for the data, you would find positive values for river flows, values close to 0 for rainfall. But in any case, you will see that the upper bound is 1 and the lower bound is -1. It can be proved mathematically. I'm not proving it. I'm just inviting you to try to make an experiment, and you will see that if you compute this coefficient, you can't get values that are below, that are outside this range. Absolute value of rho L is less or equal than 1. Another issue that you could ask me is what is the typical value that you could take for L? There is no limit. First of all, this is symmetric. If you take a negative value of L, rho of minus L is equal to rho L. You can easily check it. And you can take 0. But if you take 0 as log, again, if you take log 0, what would you expect when you measure the correlation, the dependence of a variable from itself? You would expect to find the maximum memory. So you would expect to find a coefficient that assumes its maximum value. So 1, is it true? Okay, let's see. What happens here if you put L equal to 0? It happens that you are multiplying Qt minus Q by itself. But then you divide by the square of the standard deviation. If you remember what is the definition of the square of the standard deviation, it is exactly this definition for L equal to 0. There is a difference in this term here. It's 1 divided by n minus 1 instead of 1 divided by n. But this is a negligible difference. And basically, it's very easy to prove. If you put 0 here, you get the square of the standard deviation here divided by the square of the standard deviation is 1. And then what you expect usually in hydrology for increasing L is a decrease of the correlation. And then statisticians, what they do in order to get an overall picture, they display in a graph the correlation coefficients for increasing L. It's called, this is called autocorrelation function. And it's a graph displaying rho L between 0, 1, and -1, depending on L. And it starts from 1 at log 0, and usually in hydrology what you get is something like this. But you may also get negative correlations sometimes. Okay, so in R, what you should do is type ACF G data, and you get the plot of the autocorrelation function. So in R, it's very easy. So may take the data that I gave to you, and just by typing ACF, you get the plot done. If you do that in R, you will see that R also draws two straight lines here. And you may wonder what are these straight lines, and they represent a statistical test of independence. Namely, you are interested in knowing if there is correlation or not. I introduced this correlation coefficient and autocorrelation function by saying we must have a means to estimate whether there is memory or not. And therefore you need a statistical test that tells you if the correlation coefficient is different from 0 or not, because this is an estimate. You will never get 0. When you put numbers inside here, you don't get 0. You may get something close to 1, and then you say, okay, this is dependent. But then you may take like 0.01. Can I assume that it's 0 or not? So this is a statistical test, which basically means, in very practical terms, that if your correlation coefficient is lying within this band, then you can assume that the data are independent. If you have the autocorrelation function that is lying, like in this case, outside, then the data are dependent. And you may say that they are independent after a certain delay, which in this case is this one, L star. This is the delay after which you can say that the data have no more memory. I don't want to spend time on statistical testing because this is not our topic, but you should get familiar with the terminology. This is a statistical test at the 95% confidence level. So what R depicts to you is a statistical test at the 95% confidence level. And it's important that you know this terminology because it comes forward very frequently in the operational practice. So like, is this design reliable? Yes, at the 95% confidence level. What does it mean? It means that this test, I am providing this definition in a very not rigorous manner. So don't take me word by word formally. But I think it's, I don't want to get into formalism, too much formalism. So let me say that the meaning of a statistical test at the 95% confidence level means that the test is correct with a probability of 95%. Okay? And I also tell students in practical terms, if you get 5 coefficients over 100 that exceed these 2 straight lines, you are happy anyway. Okay, because you know it's difficult that you get all the correlation coefficients that stay within this band, even if the data are indeed independent. But if just 5 of them exceed the band over 100, then you are anyway happy. This is the meaning of a statistical test at the 95% confidence level. Some people say, instead of saying 95% confidence level, some people say 5% significance level. same meaning. Okay, you may say 95% confidence level, or you may say 5% significance level. Again, technically speaking, means that the test is correct with a probability of 95%. You may also heard people speaking of confidence levels when they talk about measurements. When they give a measurement, some people, and plus minus a standard error. Usually people say the standard error of this measurement is plus minus something at the 95% confidence level. Same thing. Okay, means that their estimate has a probability of being correct at 95%. Okay, so now we have the means to detect memory. And now let's suppose that we got in a situation where memory is there. So indeed we have to use a stochastic process, indeed we have to reproduce memory. So the next question is, how can I do that? And let me anticipate that the reply is simpler than expected, will be, but now let's make a break of 15 minutes and then I'll get back.